Okay, so we will see a discussion about the second condition, which is the fluid flow down an inclined plane. So in this situation, so the big difference between this situation and the previous situation is, in this situation there is only one plane here. So in previous condition, we have another moving plane at the top, but now we don't have any moving plane, so we let the fluid flow freely like this one. So because we have an inclination here, so the fluid will flow from the top to the bottom, flow downward like this one. Okay, and then for sure the velocity distribution will occur like this one. Okay, so and then again, because we assume that, okay, so we assume that the depth here is D. Okay, so and then the pressure is constant. So we assume that dPds is equal to 0. So here, because it is open to atmospheric pressure, so actually we assume that the pressure act on this water flow is actually can be neglected. So it is equal to atmospheric pressure. Okay, so and then please refer when you revise, do revision on this topic. So please refer to equation number 1, because equation number 1 is actually the simplified version for us based on the free body diagram that we created before, and we use equation 1 to solve these three situations. So from equation number 1, so we have this one, and then because we don't have the dPds, okay, here we don't have the value of this one, so now we have the value of minus mu over minus gamma over mu and sine theta. So I think you know this one, because we already discussed about the sine theta. It replaced the dz ds, and then we give the negative sign because it going downwards. Okay, and then we give the boundary condition to solve that problem. Okay, because you know, we have the quadratic differential form here. So we have d square u over dy square. So, and then we need to integrate 2 times. Okay, so and then to get to solve that integration, so we need to substitute the boundary condition value. So this boundary condition value is actually depends on the situation that you have. So in this situation, so
Doctor,
yes.
why du dy appears or occur when the y is d? When the on the
Okay,
surface show du
I,
dy.
I'm going to explain that.
Oh, okay.
Okay. Okay. So the boundary condition is actually depends on the situation. So sometimes you need to study the situation very well. Then I hope you have capability to write down the boundary condition. So for this one, for example, the first condition is might be straightforward. You could imagine that at y equal to 0, so u is equal to 0. So means at this point, so the y is equal to 0, and then the u is equal to 0. So it's quite straightforward. And then as you ask me this one, so why we take du dy is equal to 0 and y equal to d. So at y equal to d here, okay, so actually the velocity here is equal to the capital U, the free stream velocity. Okay, so means that you have two choice, whether you want to write y at y equal to d, the u is equal to free stream velocity, the capital U. But at some situations, so especially this one, we found that the idea using u is equal to capital U is actually that it's not helping us, because we have problem with du dy, and then we start to substitute with one parameter which can create us with another unknown parameter, because in this situation we don't have any information about capital U, about free stream velocity. Okay, so that's why in this situation, okay, it is advantage for you. It is advantage for you to take du dy equal to 0. So what is the meaning of du dy? Means the gradient of velocity is equal to 0. Means at y equal to d, here, the u mean the local velocity at this point is not going to change anymore. Okay, so means that first you should understand that du dy means changes of u along the y-axis. So this is the y-axis. So start at this point, we found that the velocity of this one by right is not changed. Okay, so so in reality, we could say that there are no liquid at this point, so means there are no changes anymore. So means the velocity of u, the velocity at this point is actually will become constant at any y, at any d. So that's why we could say that the gradient du dy is not exist anymore, so it's equal to 0 at y equal to d. Okay, can you understand that meaning?
Yes, Ken, thank you.
Okay. So and then so I simplified this one. So you need to integrate this equation 1. So you have this one. So and then after we substitute the value. So this is actually, if you try to integrate this one, you will ease your calculation, because you already have the value of du dy. So and then you could substitute this one. So and then you get, when you integrate, you could get another unknown. So another constant c here. So, and then what you need to do is you keep, okay, first you use this one. Okay, and then you will get this one, and then you need to integrate it one more time, and then you substitute with this boundary condition. Okay, so this what I say here. So when u is equal to capital U, it also can be assumed that du dy is equal to 0. But this is the trick for you to solve that problems. Go. So and then if you substitute with the boundary condition, so you will find that the c is actually you will have a value of constant c. So you substitute with this you substitute here. Okay, so you substitute. Okay, so maybe I'm lost here. Okay, so you get the c here. So and then you substitute the value. You get this value. So and then you simplify that one into this term. So and then you integrate for the integrating for the second time. So you will have this one, and again you will have another constant here. So you substitute with the value, and finally you will get the value of c equal to 0. And then finally you will simplify, or you could produce the value of u here is equal to this term. Okay, so here, okay, because we have mu here, so we have gamma here, which is rho and g. So and then we have mu here, so it is divided by mu. So and then I think you already know if the rho over mu here is actually equal to the nu. So, in some textbook they will show in terms of this one, and some textbook they will show in terms of this one. So I hope you could understand the changes of the equation, because some writers like to use the kinematic viscosity. Okay, and then another one, we need to calculate the density and also the mu. So it depends on the situation. So sometimes if sometimes might be to simplify the calculation, you just find the kinematic viscosity, then you could solve this problem by using this equation. Okay, now this is an extra discussion. So we try to find what is the average velocity, and then we try to calculate what is the flow rate that flow on that slope. So the resulting profile is a parabola with a maximum velocity occurring at the free surface. Means here is free surface means surface of water that make contact with atmospheric pressure. So we have an inclined plate like that one. So and this is the fluid. So because we don't have any plate at the top, so the surface of this one is directly contact with atmospheric pressure. So this situation is called a free surface. Okay, so it can occur in flow-in pipe. Please be careful. So for example, if your pipe is your normal pipe is circular shape, so that's why if you are calculating flow-in pipe, before you determine to use whether it is suitable with a flow-in pipe equation or not, first you need to determine whether the fluid inside that pipe is fulfilled all or not. If there is only half of them, or mean only a part of this pipe is filled with water, so you are not allowed to use the idea of flow in pipe. So in this situation, actually, you are using the second condition of this one. So because this condition is also called as an open channel. So the open channel means the water flow at a water flow with a free surface. So free surface means there is a surface of water here, which is direct contact with atmospheric pressure. Okay, so this is the meaning of free surface. So so we assume that the u velocity u is maximum at y equal to d. Why it's maximum? Because the slip or the shear stress is the weakest one, because it is far away from this solid surface, and the interaction is, okay, for example, this is the surface, so this is the last molecule, so this is the second last molecule. So mean the second last molecule will interact each other in terms of liquid molecule with liquid molecule. So the shear stress is quite bigger compared to the shear stress that occur between the liquid molecule with gas. So this is an air atmospheric pressure. So means that the shear stress here is the weakest one. So that we assume that this velocity will flow at maximum velocity. So at y equal to d. So and then if we substitute with the previous equation that we have here, so we substitute y here with equal to d. So we could get this term. Okay. So and then to calculate the flow rate. So normally in second situation, so normally we need to calculate the flow rate, because the open channel situation, so it will reflect about the drainage, about a river, and so on and so forth. So it is sometimes it is important for us to know the flow rate of that channel. Okay, so the idea of flow rate is Q is equal to AV. However, because our velocity distribution is not constant, so if we could see here, so the velocity is changing. So that's why we need to solve the idea of flow rate by using this idea. So means U here is reflect the value of V, and the A here is the dy. Why? Because we assume that we have the velocity distribution like this one. Okay, so we take a very small area. Okay, now we calculate the flow rate for this small area. So they assume that the flow rate for that small area is small q. So it is equal to the u times dy times width. So at this situation, we assume that the width here is unity. So it is okay for us to calculate as dy because the width is equal to 1. So and then to get the total flow rate, so we integrate both equation. So and then we assume that the integration of small q here will give us a capital Q with which shows the total flow rate that occur on that situation. So and then the limit, because we are integrating in terms of y-axis, so the limit is from d to 0. So I think you know how to choose this one. So we substitute the equation that we have. Okay, so and then so this equation actually from the u here. So so we substitute the value of this one. Okay, now not the value of u max, because u max is only occur at y equal to d. So we substitute this one. So and then we integrate it into dy. So we substitute the limit dy, and finally we could get this. So this is the total flow rate. And then we also could get the average velocity. So the average velocity means that, okay, we know that the velocity distribution is like that. So it is not easy for us to do the calculation if we need to change the velocity every time according to the height of this one. Okay, that's why in undergraduate study, might be you are using the average velocity to solve problem. So that average velocity actually must be synchronized, must be tally with the flow rate. So means that you should start to calculate this one by from the velocity distribution like this one. You need to calculate the flow rate according to the velocity distribution. And finally, when you get the total flow rate from the velocity distribution, then you are managed to calculate the average velocity. Why? Because you need to make sure that you could get the same velocity, the same flow rate, whether you calculate using the velocity distribution of this one or by using the average velocity. So from the total flow rate here, so we could calculate the average velocity by using this equation. So we have Q divided by A. So finally we could get this one. So for the cross-sectional area here, it is okay for us to calculate the real cross-sectional of this flow. So because the width here is equal to 1, so then we divide with the value of d only. So if we divide with d, so the d cube here we reduce into d square. So that's what we get here. Okay, and then the nu here is actually changes from the gamma here, the g, rho and g with the mu. So I hope you could understand all these terms. Okay, so this is simplification that always done by the open channel researcher. So first, sometimes they substitute the value of S naught equal to tangent theta to replace the sine theta. So this is the common assumption, okay, because the slope is very small. So why slope is very small? So this is the reality about open channel. So open channel means research about the drainage, river, and so on and so forth. So if you are civil engineering, if you are a civil engineer, you are going to design your sewage or drainage or whatever to drain water in with a free surface. So you may design the slope in very little degree here. Why? Because if the angle is very high, for example, 3 degree, so your water velocity will become high and it will start to erosion. So, and then that one is erosion, and another term, it is not easy to find a path with a high angle here. So for example, if you want to create drainage for a town, so normally for a town, the landscape is horizontal. So it is impossible for you to create drainage with a 3-degree slope. Okay, that's why we could make assumption of tangent theta is almost equal with sine theta for a small slope. So, and then if you calculate the Reynolds number and so on, so you found that the laminar flow, okay, the laminar flow in this situation, okay, must be less than 500. Okay, because this is an open channel. If you open textbook about open channel, you will found that the limit for laminar for open channel is less than 500, and if it's greater than 2000, it is already in fully turbulent. Okay, so this is the okay, I also write down this one. So it is also known as open channel problem. So in open channel, you may derive this equation according to the Bernoulli equation, because we are discussing about the liquid, and at that time we use the idea of tangent theta. Okay, but this is just the discussion of this one. So the most important one is to derive the velocity distribution, and to take what boundary condition that can be used to solve the velocity distribution. So, and then we go for the third. Okay, this is the example. So I think we could go this one because you could download this one, I think. So I think I skip this one. So this is just a very straightforward. You have the numbers, you will substitute with this equation, and finally you will get the total discharge or flow rate for these problems. Okay, so this is the third situation for Couette flow. So it is flow between stationary parallel plates. So this is, if you see at situation number 1, so we have a plate. So, and then normally in horizontal, okay, because in horizontal there are no, the fluid cannot flow by itself. So because it is no slope. So the fluid will flow, the fluid will move because the top plate here is moving at certain velocity. And the second one is we have an inclined plate there, but we don't have any top plate. So, and then the flow now will flow at certain velocity. And at the third situation here, we have two plates, but the plates is fixed, not moving. And then because we have a slope here, so we could say that the velocity here, that the fluid will flow at certain velocity. Okay, this is the third situation. So, and then I think you already know how to draw the velocity distribution. So, because we have no slip condition here, the molecule stick very hard on the surface. So the velocity will become like this one. Okay, and then at this situation, we could assume that at the center point here, the velocity is the maximum one. Okay, and then okay. So first, I think you already know, we start calculate with equation 1, and then we need to know the boundary condition. So again, the boundary equation is not a condition that it's not worth for you to remember, because it's changing depends on the situation. But I hope you could remember the tricks to get the boundary condition. So here we could say that at y equal to 0, so the velocity is 0, and also at y equal to b, the velocity is equal to 0. So this is the boundary condition that we have. And please do not afraid the velocity of u equal to 0 comes twice, because sometimes students think, oh, this might be something wrong here, because the zero will sometimes create troubles in our equation. But it's okay for this one, okay, because based on the diagram here, okay, both location will give us zero in velocity. So and then we come back with the equation 1 here. So and then we integrate 2 times. So and then finally we could have two constant, which is C1 and C2. So I hope you could do this at home. So and then we substitute the boundary condition, which is u equal to 0 and y equal to 0. And then we get that C2 is equal to 0. Then we applying boundary condition u equal to 0 at y equal to b, and then we could get that the C1 is actually equal to this term. So and then we need to substitute back this C1 into this equation, and finally we could get the velocity distribution like this one. Okay, so here, so we have you have dz and ds here. So you could simplify it as dh ds, because according to this diagram, so we have a h. Right? So we have the, okay, so we replace the b with h. Okay. Let me see. Okay, I think that is the reason. So and then this is the discussion. So and then we assume that the maximum velocity occurring at y equal b over 2, mean at the center point, okay, the velocity will become maximum. So we could we substitute the value of y equal b over 2 in this in this equation. So we could find the terms of u max is like this one. Okay, so and then if we want to substitute with if we want to use the dHds here, okay, so and then okay, so we in term of, okay, what I want to say here is actually if we test the pressure, okay, so we found that it will give us the negative term. So the negative term here means that I'm sorry, okay. So this is the inclined terms, okay. So and then if we have velocity, okay, and for this situation, we found that the flow rate, the Q will be constant. So this is the rule of thumb of fluid. So the flow rate is constant, and because our cross-sectional area here is constant, means at inlet and outlet, the cross-sectional area is constant. So Q is equal to A times B. So and then if the A is constant, so means that the velocity will remain constant too. So it means that the velocity here will remain constant along the path of this one. So means that, and in reality, I think you already know about the Bernoulli equation. So if we derive it with a Bernoulli equation, so let's say we have the point 1 here. So let's say this is point 1 and this is point 2. So in Bernoulli equation, so we have the energy, or we could say it's the Bernoulli equation at point 1. So Bernoulli equation is P over rho G V square over 2G and Z. Okay, so this is for point number 1, and it is equal to Bernoulli equation at point number 2. So we have P over rho G plus V square over 2G plus Z at point number 2, and we need to add with losses. So we have the HF here, losses. Okay, this is equal to losses. So I think you already know about this one. So you learn about the major loss, minor loss, and so on and so forth. So means that However, no, even though the velocity is constant, but the pressure will become lower and lower. Why? Because a part of that energy is actually convert to overcome the losses. So we have the pressure here. Okay, so we have the pressure here, the pressure term. So normally the pressure will become lower and lower because a part of that energy is actually to overcome the losses. Losses mean the resistance that occur when fluid move from one point to another. Okay, that's why if you work in terms of if your work's nature is about to analyze flow in pipe, about oil and gas and so on and so forth. So might be you are familiar with term of pressure loss, or you what we call it as, I think, pressure loss. Okay. So means that at certain time for every 10 meters, for every 100 meters, for example. Oh no, bukan pressure, not pressure loss, pressure drop. So pressure drop means the decrement of pressure. So normally we reflect the situation like this. Okay. So by the terms of pressure drop. So pressure drop means the pressure is become lower and lower. So that's why in these terms, they will give you that DHDS in negative. Okay. So it's showing that it's the decreasing of piezometric pressure. So piezometric pressure means the pressure if you measure it by using the piezometer. Okay, piezometer or manometer. So it's reflect the same things. Okay. So again, so this is the basic idea. I already explained this with the second situation. So we need to calculate the flow rate. So we integrate u dy with limit of 0 to b. So and then we could get this term. So and then finally to get the average velocity with the same reason to make sure that our average velocity will give same flow rate compared to will give a same flow rate. So we divide flow rate with B. So again, so we just divide by the height of the plates because the width is 1 unit. So we will get it is equal to 2/3 U max. So this is the common assumption that used in undergraduate might be. So we could understand that we could make fast assumption, fast calculation about the average velocity by take 2/3 U maximum. So so this is the example. So I think you could read this one and then you could solve it. So you just substitute value in equation. So finally we could have the value of the piezometric head. So this is actually to reflect the pressure drop.